Alright guys, welcome to lesson 6.7. It's going to actually be a 2-day lesson. I just put all the notes together as one thing, but you can just submit the first half of your notes for day 1 and the second half for day 2. But the entire thing is in one handout here. Alright, so what are we going to be talking about for these next 2 days here? We're going to be talking about these things called integral functions. So you guys know what a function is, right? A function is something where you plug a number in, you get an answer out. Well, an integral function is a function that actually has an integral inside of it. It's kind of interesting, huh? So it's a function where you plug something into an integral and you get an answer out of it. So today we're going to learn how to evaluate these things. We're going to learn how to look at their graphs and identify various qualities about those graphs. Okay? So a lot of things we'll do, a lot of things. So let's go ahead and talk about the integral function first of all. All right, so our integral function here is called g of x. This is called an integral function because its formula has an integral in it. The bottom number here represents just a number in this case. It doesn't have to be just a number, but in this case it is. But somewhere inside the integral's limits has to be an x, the input variable. Okay, so basically when you plug a number in for g, like let's say you plugged in 6 here, then you would be plugging in 6 right here. Now these variables over here, a lot of times I don't even use x for those spots. I just use some other variable t. It doesn't matter what variable you use there because they actually don't matter. And we'll kind of get to why those variables don't matter later on. But the one that really matters is the one that's right here. That's my input variable. So when you plug a number in for g here, you're plugging a number in here. And whatever goes on the bottom here, it could have an x in it, or it might not. It might just be a number. But the point is that somewhere one of your limits has a number here. So I've titled this here the area accumulation function. So let's see why I would call it an area accumulation function. So I'm going to do a little demonstration here on Desmos to kind of demonstrate for you why I'm calling it an area accumulation function, and also to give you a little bit of an intuition about what integral functions do. So first of all, let's go ahead and create a function here. So I'm going to pick the function here. F of x equals sine of 2x plus 2. Just random function, but there it is. So I'm going to go ahead and graph it, and that's what the graph of that particular function would look like. All right. All right, so now let's go ahead and do an integral of this function. So I'm going to make an integral of this function here. I'm going to take my f function and take the integral of it. Now, as you guys know, an integral represents the area under the curve from a to b. So for now, I'm going to go ahead and I'm going to let a equal to -2, and I'm going to let b equal the same thing, so they have the same starting point. And then I'm going to show you the area. Now, for now, let's go ahead and say b is at -2, so my first point is going to be at -2. But let's let a go up to like 0, like maybe like right about here. And as you guys can see, we have the area function. Or we have, well, not an area function, but we just have an area from -2 to 0, and that's a fixed area. But what happens if I let a and b become variables? What happens if a and b are constantly changing? Well, if a and b start changing, then the area is going to start changing. So let's go ahead and start changing my upper limit here first, -2. As you guys can see, as b changes, the area changes. So we can also let a start to change. Both the upper limit and the lower limit can move around. And that causes the area, which you guys see here in this gray box, to constantly be changing. Okay? And so this is what we would call an area function because the limits, a and b, are variables themselves. And they're constantly changing. And so as the variables change, then the function changes. So why do I call this an area accumulation function? Well, because like if we just let a be set at -4, you guys can see here that if I just let b become greater and greater, we accumulate more area as b increases. So it's an area accumulation function because the limits are changing, and since the limits are changing, the area is changing. And so that's what a integral function is. It's an area accumulation function where you're plugging in numbers for x, and x is one of your limits. And as x changes, the area changes, and you begin to accumulate area. So this is what we call an area accumulation function. Okay, so that is what a integral function is. All right. So now I want to introduce you guys to something known as the second fundamental theorem of calculus. Let's go ahead and begin here. This is just an introduction to it, but as you guys can see up here at the top, I've given you guys an integral function. How can you tell that this is an integral function? Well, it's a function where the x value is in the place of the limits. So, first thing we're going to do is we're going to use the first fundamental theorem of calculus to write g of x as a function of x. So what do I mean by that? Well, the first fundamental theorem of calculus tells me that if you have a function and you're going from a to b, you go ahead and you integrate this function, and once you integrate it, you plug in the upper limit and the lower limit and subtract them. So that's what I want to do first. So I want to apply the first fundamental theorem of calculus to this problem here. So g of x is equal to the integral of 2t dt from 0 to x. So first of all, let's integrate this. What is the integral of 2t? Well, hopefully you know that that's t squared. Next, we plug in the x and the 0 and subtract them, right? X squared minus 0 squared is x squared, and there's my answer. So, I just found out something. I just found out that g of x is equal to x squared. So, if g of x is equal to the integral of 2t dt from 0 to x, you could just apply the first fundamental theorem of calculus to rewrite g of x as a normal function by actually integrating this and rewriting it without integrals. So there's two ways that you could write this then. G of x is equal to this, but that's basically the same thing as this because of the first fundamental theorem of calculus. Right? But now, number 2 asks us to use our answer from part 1 to find the derivative. So if g of x is equal to x squared, then what's g prime? Well, that would just be 2x. Now that 2x should look familiar. 2x and 2t. Why are those exactly the same? Well, surprise, surprise, it's always going to turn out to be exactly like that if you follow this process. If you integrate the function and then take the derivative of it, you're going to get right back to where you started. If you integrate 2t, you're going to get a square. And if you take the derivative of that, you're going to get back to where you started. Why? Because integrals and derivatives are opposites of each other. But something interesting did happen here along the way, in case you didn't notice a slight little difference. They're not exactly the same. They do have a slight difference. This has a t in it, and this has an x. The reason for that is because when you do the fundamental theorem of calculus, after you integrate that, you plug these numbers in, right? And so the t becomes an x or a 0. Okay? So here's the second fundamental theorem of calculus that we've been building up to. If you have an integral function that looks like this, where you have a number on the bottom and a variable on the top, then and you're asked to find g prime which is, the thing that we're looking for here in this case, well, g prime is going to basically be what you started with in here anyway. It's just that instead of a t, it's going to have the variable you're plugging into it. Okay. Now you could do it the long way. The long way would be to integrate it and then take the derivative, right? But the short way is to use the second fundamental theorem of calculus, which basically says that if you take the derivative of this integral, you just get the original function. You can also think of it like this. If you have an integral of a function, and you take the derivative of that function, this and this cancel each other out, but the x drops inside. Why does that happen? Well, because of the first fundamental theorem of calculus, but also because derivatives are opposites from integrals, so they just kind of undo each other. But in the process, it does drop the x in because of that first fundamental theorem of calculus that's part of the process. So there's your idea. So that's the second fundamental theorem of calculus. Let's go ahead and take a look at some examples here. So, using the second fundamental theorem of calculus, find f prime of x. So, I have an integral function defined here. It's f of x. F of x is the integral from 1 to x of the function 2t to the 1/2 power. I want to find f prime of x, right? Well, the derivative basically is going to do two things. It's going to cancel out the integral, but in the process, that x is going to drop in the t place. And so it just ends up being this. Okay? Same thing over here. If I want to find f prime of x, the derivative is going to cancel out the integral, but the x is going to drop into the t place. And you're done. You guys are like, Bailey, it can't be that easy. It is. It is. All right. So that is what we call the second fundamental theorem of calculus. So, I'd like you guys to look at your homework worksheet for 6.7a. I'm calling it 6.7a because, like I said, this is going to be a 2-day lesson. So your homework's going to be split up over 2 different days. The first day I'll call the worksheet 6.7a. The second day I'll call it 6.7b. So you're going to be looking at worksheet 6.7a, and I want you guys to do homework problem number 1. Pause the video here. When you unpause it, I will reveal the solutions to you. All right. So if I want to find the derivative according to the second fundamental theorem of calculus, the derivative of this is going to cancel that integral out, and that x is going to drop in where the t is. So it's going to be x squared plus 4t minus 1. For number 2, when you take, I put an x, that's supposed to be an x, not a t. When we take the derivative, the integral cancels out and the x drops in where the t was, and so we have negative 4 over x plus 3 cubed. So far we've learned 2 things. What an integral function is. It's an area accumulation problem. But we've also learned that its derivative is basically just the function that's on the inside there, and that function is dependent upon x. Put a t there again. Its input is basically dependent upon the x, the variable up here that's constantly changing, and that would be the rate of change of that area accumulation function. Now earlier, remember how I mentioned back a few slides ago that this variable right here didn't really matter, the t, what it is? Well, the reason why it doesn't matter is because it just goes away when you do the process. The t just gets replaced with this x. So we call it a dummy variable in this case because it really doesn't have any effect on anything. All right, so let's move on and develop some more concepts here in dealing with area accumulation functions. Let's review some stuff here. If you have a function g, when it's increasing, that would mean that its derivative is positive. When it's decreasing, its derivative is negative. When you have a relative maximum, that means that g prime goes from positive to negative. And when you have a relative minimum, that means that g prime is going from negative to positive. Okay? So that applies to integral functions as well. Okay? But here's the cool thing about this. the derivative of my function, in this case g prime of x, according to the second fundamental theorem of calculus, what would g prime be? G prime is going to be the cancellation of that integral with the x dropped in. So in this case, g prime is just equal to f. Okay, so keep that in mind. That's going to come in handy when we do these next few problems here. So let's take a look at example 2. We need a little bit more window space. Okay, so the graph at the right is the graph of f. And I'm telling you, g is an integral function of f. G is the integral of f from 0 to x. All right? So, if g of x is equal to the integral from 0 to x of f of t dt, then, because of the second fundamental theorem of calculus, g prime is equal to f of x. So the derivative of this integral function over here is this graph. That graph is the derivative of g. So you can think of that as a derivative graph. Remember back in Unit 5 we talked about graphs of derivatives? Well, we're looking at the graph of a derivative in this case. We're looking at g prime, which is equal to f. So let's keep that in mind. So we know now that f is the same thing as g prime because of the fundamental theorem of calculus. So now the question here is, where is the graph of g increasing? Well, g increases when g prime, which is the same thing as f, is positive. This happens where? Well, anytime this function here is above the x-axis, that would mean it's positive. So right here, f is positive, and right here, f is positive. And when f is positive, g prime is positive because they're the same. So this happens on those two green intervals that I have there, which is from -6 to -4, and from 2 to 8. So g increases when g prime, which is the same thing as f, is positive. This happens on the intervals -6 to -4 and 2 to 8. Let's go ahead and take a look at another one, part B. Where is the graph of g decreasing? Well, g decreases when g prime, which is the same thing as f, the graph above, is negative. This happens anytime my graph is below the x-axis, which is on the intervals from -4 to 2. Okay? So this should look a little bit familiar. This should look like the stuff we learned in Unit 5 because it is. In Unit 5, we talked about looking at the graph of a derivative and using that to talk about where a function's increasing or decreasing or where its relative extrema are. But in this case, it's just not obvious you're looking at a derivative function because it's not written as a derivative, but it is the derivative of this function. All right, let's go ahead and take a look at C. Where are the relative extrema? Well, for part C, G has a relative max when G prime, which is the same thing as F, goes from positive to negative. This happens where? Well, if G prime, which is the graph above, is going from positive to negative, that means it goes from being above the x-axis to below. So where does this line go from being above the x-axis to below? Well, that happens right there at -4. Furthermore, we could say G has a relative min when g prime, which is equal to f, goes from negative to positive. This happens at x equals what? 2. At x equals 2, the graph goes from being below the x-axis to above, which means that f is going from negative to positive, which means that g prime is going from negative to positive, and when g prime goes from negative to positive, that means that g has a relative minimum at that point. Okay, so you'll notice that these explanations are almost identical to the explanations we had in our Unit 5 section. But there is one little difference. Instead of just saying g prime goes from positive to negative, I am stating that g prime is equal to f, which is this function they gave me. So that's the one little difference that I'm noting there. You know, your explanation needs to make a connection between this function, which is the one the questions are being asked about, and this graph, which is the stuff you're using to answer those questions. Since they're not the same thing, you do need to make a connection between them by stating that, well, this graph is the derivative of g. So, but other than that, the explanations are pretty much the same. All right, let's go ahead and take a look at your homework problems now. Go to homework problem number 5 on worksheet 6.7a and do parts A, B, and C. And when you unpause the video, I will have the solutions up and available for you. All right, I'll let you guys go ahead and study my answers here, and then we'll move on to the next part of our lesson. So let's go ahead and chat about some other review stuff. Now, g is concave up anytime the second derivative is positive. Okay, so g is concave up anytime the second derivative is positive. Now, we've already said earlier that g prime is equal to f of x, right? So g double prime is the derivative of f prime. Now, today, since we're going to be looking at a graph of f prime, when would f prime have a positive slope? Because that's what this would be. This is the slope. Actually, let me back up a little bit. This is the slope of f prime. Okay, g double prime is the derivative of f prime, which means that g double prime is the slope of f prime. So when g double prime is positive, that means that g prime is increasing. So let's go through that logic again one more time. When g is concave up when its second derivative is positive. Since the second derivative is the slope of the first derivative, if the second derivative is positive, that means the first derivative is increasing. Okay? So let's go through the next part of this. G is concave down anytime the second derivative is negative. Now, the second derivative is the slope of the first derivative. So if the second derivative is negative, that means the first derivative has a negative slope, which means that it would be decreasing. G has a point of inflection anytime the second derivative, I don't want to put equals there, I want to put changes signs here. So erase that on your notes and put changes signs, because it actually could be undefined. It doesn't have to be 0. It could be either 0 or undefined, but the point is that it's changing signs. So, and actually I shouldn't say it. G double prime is changing signs. So the function g has a point of inflection when the second derivative is changing signs. Well, if the second derivative, which is the slope of the first derivative, is changing signs, that means that g prime is going from either increasing to decreasing or from decreasing to increasing, which means that it's potentially either a relative max or a relative min of f of g prime, right? If g prime is going from increasing to decreasing, that would give you a relative max. If g prime is going from decreasing to increasing, that would give you a relative min. So if g has a point of inflection, that means the second derivative is changing signs, which means that the slope of g is changing from either increasing to decreasing or decreasing to increasing, which means that it will potentially be either a relative max or a min on the graph. Okay, so Lots of stuff there. Let's go ahead and put that to use. Example 3. The graph at the right is the graph, once again, of g of x given as an integral function of f from 0 to x. And here's a graph of f. Now, it will be helpful for us to remember, and just write this up here at the top, that g prime is equal to f of x, and g double prime now is equal to f prime of x. In other words, the slope of our graph. That'll be helpful to remember. So let's go ahead and take a look at part A here. Where is the graph of g concave up? Well, g is concave up when g double prime is positive. Now, a shorter way of saying is positive, if you want, is just to put greater than 0. Okay? So g is concave up when g double prime is greater than 0. G double prime is greater than 0 when g prime, the slope, when g prime, which is the same thing as f, is increasing. This happens where? Okay, so let's reread it again. Real quick, let's go back to our last slide to kind of help make sense of all this. G is concave up when g double prime is positive. G double prime is positive when g prime is increasing. And remember, g prime equals f. Okay? So keep that in mind. That's my explanation there. So g is concave up when the second derivative is positive. G double prime is positive when g prime, which is the same thing as f, is increasing. So where is this graph increasing? Well, I see it's increasing right here on this interval. In other words, it has a positive slope. And that's from 0 to 4. All right, let's go take a look at part B. Part B, the graph of g. Where is graph of g concave down? Well, g is concave down when, maybe you guys could predict what I'm going to write here, when g double prime is less than 0. And g double prime is less than 0 when g prime, which is the same thing as f, is decreasing. This happens on what interval? Well, from here to here it's decreasing. And so we would say from -6 to 0. You'll notice that over here, the function is not increasing or decreasing. So if g prime, which is f, is not decreasing or increasing, well, then that would mean that g cannot be concave up or concave down. All right, let's go ahead and take a look at the last one, part C. Where are the points of inflection? G has points of inflection when g double prime changes signs. G double prime changes signs when g prime, which equals f, changes from increasing to decreasing, or vice versa. You don't have to say both, you can just say vice versa. This happens where? Where does this graph of f, where does f change from being increasing to decreasing or vice versa? Well, right here, we're changing from being decreasing to increasing, and that's the only place. I don't see anywhere else. So it happens right there at x equals 0, and that would be my point of inflection. So G has a point of inflection when the second derivative changes signs. The second derivative changes signs when G prime, which is f, this graph up here, changes from either increasing to decreasing or vice versa. And this happens at x equals 0. All right. So let's see how you guys do with one of these now. On your homework, go ahead and find number 6 and try these 3 questions. When you unpause the video, I will have the solutions available for you to check your work. All right, so there you guys go. Go ahead and study those answers there and see if you guys agree. If not, let me know in class and we'll talk about it. The last line here on the bottom says, so G has no points of inflection. All right, let's go ahead and move on to one more topic for the day. All right. The graph of f of x is given at the right. On the interval from -6 to 2, we have a linear function. So they're telling us that this is a straight line. On the interval from -2 to 0, we have this parabola equation here. And on the interval from 0 to 8, we have a semicircle. Okay. Now they're telling us, once again, that we have another integral function. This one's different than the ones I've been using previously throughout the class. So they want me to find g of -6. Let's go ahead and begin there. So we know that this is my integral function, right? They tell me this is a graph of f over here once again. All right. Well, they're asking me to find g of -6. Well, what that means is they want me to plug -6 in for x right here. And what this is this is the area under the curve from -2 to -6. Now, first of all, before we begin, I want you guys to notice that these are backwards here. This is big. -2 is bigger than -6. So we're going to use property 2 here really quick to fix that. That's kind of like a little uninvited guest who thought he would show up in this lesson. But there he is. So property 2 says I can switch those around if I put a negative in the front. So you do want to make sure that your smaller numbers on the bottom, okay? But basically, we're finding the area under the curve from -2 to 6. So basically, that would be this triangle right here. So the base times the height, that'd be 4 times 4, which is 16, cut in half, which is 8. And so the answer here would be 8. But since there is that negative in the front, because we had to apply property 2, the answer is -8. Okay, so basically just plug it in and then find the area under the curve. Make sure you use the properties when necessary. Let's look at another one here. Let's do g of 0. Well, this time I don't have to use a property to flip it around. -2 is smaller, so we have it in the right spot. And we want to go from -2 to 0. Now, this is a parabola, you guys. There's no geometry formula for that. Okay, so in this case, we have to actually take the function they gave us. Remember, they told us that from -2 to 0, that's the interval we're on right now, -2 to 0. For -2 to 0, that's my function, 4 minus x squared. So since I can't use geometry this time, we're going to have to integrate it unit 2 style. And that means basically fundamental theorem of calculus. Okay, so here we go. The integral of 4 is 4x, and the integral of x squared is x cubed over 3. And then we're going to go ahead and we're going to plug these numbers in. And I'm not going to simplify it this time. And I don't care if you do it or not either, honestly. It doesn't really matter. Just want to make sure that you guys know how to do the problem. There you go. So in this case, we're doing the fundamental theorem of calculus. All right? Because we can't do geometry. But I did give you the actual functions equation from here to here. So since we're finding the area there, that's what our answer will be. Now, just in case that comes in handy a little bit later, I'm gonna record these findings that I'm getting as I go. It might come in handy later. I don't know. We'll see. But here we found this was 8. Now I know we said it was -8, but that was for the problem. This area is actually 8. But when we did this one, since that particular question had property 2 applied to it, it became negative. But on the graph, it's still positive here. And I used my calculator to find this area just now. I didn't want to do the work by hand. And what I got was 5 1/3 or 5.3 with a little bar over it. So I cheated, used my calculator. All right. So let's go ahead and move on to number 3. I don't know if those numbers are going to come in handy later, but I'm just writing them down so we have them for later. Let's do g of 0 or g of 8 now. That's for number 3. Okay, so I want to go all the way from here, -2, all the way up to 0, and then pass that on to 8. So I want to get that area there. So I want to get those 2 half pipes plus that parabola. So I'm glad that I wrote that down now because I do need that 5.3. I'm going to be using that. All right, so this integral here is basically going to be all those areas added together. So we already know that from here to here is 5.3 bar. We did that already. But we also need to find the other 2 areas. Now, as you can tell, this area here and this area here, they're identical. So I really just need to find one of them and write it twice. Now, I don't know if you guys remember how to do that, but basically if you want to find the area of a half pipe, what you're going to do is you're going to find the area of a square and subtract from it the area of a quarter circle. And what will be left is the half pipe. So in this case, my half pipe has a height of 4 and a base of 4, which means that my square will be 4 by 4, and the radius of my semicircle will be 4. So the area of the square here is 16, and the area of a quarter circle with a radius of 4 would be pi r squared divided by 4. So that would be 4 pi. So that's one of the half pipes. So 16 minus 4 pi, and then 16 minus 4 pi. They're both the same. It's just that one's backwards, but it doesn't matter. They're the same kind of shape. So we could add all that together and get a decimal. That might come in handy later. I don't know. For now, I think I'm just going to leave it. I'll just bring it back if I need it later, but for now I'm going to leave it like that. So there's the answer to g of 8. Let's go ahead and take a look at g prime of 4. Now notice there's a change now. We're talking about a derivative. So g prime of 4. Well, the first thing I want to do is I want to find g prime. So what is g prime? Well, using the second fundamental theorem of calculus, if you take the derivative of an integral function, the integral goes away and the x drops in, and you just end up with f of x. So g prime of 4 is f of 4. And that's basically just the y value on this graph when x equals 4. What's the y value when x equals 4? 0. All right, let's do another one. G prime of -1. Once again, g prime of x is f of x. So g prime of -1 is f of -1. In other words, the y value when x equals -1. And in this case, that would be 3. So we're not doing area anymore when you do the derivative. These are area questions because those are integral function questions, which are area accumulation problems. But the derivative of an area accumulation function is just the graph that we're looking at. So you just need to pick out the y values that are on there. Let's do one more. G prime of 0. Well, G prime of x, once again, is f of x. So G prime of 0 would be f of 0, and f of 0 is 4. All right, let's go ahead and do number 7. Last one. G prime of x is f of x, right? But this problem is asking us about G double prime. Well, G double prime of x is f prime of x. The derivative of one side is the derivative of the other, right? Now this is the slope of f. So whenever I say find G double prime of negative 4, I'm asking you what is the slope of f. In other words, f prime of negative 4 at x equals negative 4. So let's find negative 4. It's right here. What's the slope of that line? Well, the rise is negative 1 and the run is 1. So rise over 1, negative 1 over 1 is negative 1. The slope of f. So when you see that, they're asking basically in this case for the slope of f. All right. Let's go ahead and toss one of these your way. Homework problem number 7. You guys are going to do A through G there. And when you unpause the video, I will have the solutions up for you. All right, part C was a little bit tough. We'll talk about that. For part A, G of 1. So we're starting at negative 1 and ending at 1. So that would just be the area of this rectangle, which is 2. G of negative 5, you would have to apply property 2 to this one. So you start off by writing it like this, but then you have to flip it around because we want that negative 5 on the bottom. So you have to put a negative in the front. And so we're finding the area from here to here. This is a positive 0.5. This is a negative 4.5. Put those together and you get negative 4. But I forgot to change it back to a positive because this negative in the front cancels out the negative. So you actually end up with a positive 4 there. Okay. Part C is a little bit tricky. I'm asking you to find the area from negative 1 up to 2. So starting from negative 1 to 1 is a rectangle, but from 1 to 2 is the area under a parabola. They tell us that f of x is equal to x squared from 1 to infinity there. So we already know that this much of it's 2, but how do we find this? Well, we have to use the fundamental theorem of calculus. So I start off by writing out my problem here. And then I apply property 6 to it. Now you didn't have to do this necessarily to show your work, but it's helpful. I found this integral separately from negative 1 to 1 because that's simple. It's just the little rectangle there, and I already know it's 2. The issue is how do we deal with the other part of it from 1 to 2, the rest of that area? Well, we know that the function on that interval is x squared, so we'd have to use the fundamental theorem of calculus on this one. Now, I'm not showing my work for that, but you do end up with about 2.3. So with a bar over it, so if you had to do 2.3 plus 2, you get 4.3. So final answer there. The other ones here, I'll let you guys check on your own. They're pretty self-explanatory. But other than that, that's where we're going to stop for the day. We'll do the rest of this lesson on the following day. All right, and you guys go ahead and finish up worksheet 6.7a. We'll see you guys in class.